So I remember an introduction many years ago when I was at Toronto. A fellow named Hector Levesque, who's a world-famous Torontoanian, was giving a talk. The introducer did a great job. He said, "Today's talk is being given by a man who needs no introduction," and sat down. So perhaps I need no introduction also, right?
You're pretty much.
So this talk is sort of introductory tutorial material that is sort of a talk I've met with several of my colleagues who are interested in learning about it, and I made the point that it'd be nice to get it filmed so I could show them a movie, show them a video of this material, and they could just use that. So I made the mistake of saying that a month ago, and a few days ago they said, oh, not a few days, yesterday, they said, "Can you want to do it right now?" I said, okay. So that's why I'm here. So this is a talk on Bayesian Belief Nets. Please feel free to ask questions as I go through the material. So let me actually begin with this wonderful article that appeared, wow, over 20 years ago. There are two things I really liked about this article. One, it mentioned me. It's always flattering. And the second, it mentioned another more famous fellow, a guy named Bill Gates, who commented that Microsoft's competitive advantage is its expertise in Bayesian networks. And to back this up, he pointed to several examples of Bayesian nets that were deployed in various Microsoft products. One of them was Lumiere. It was a tool that had been developed by some colleagues that was designed to actually watch a user as he uses various Microsoft products and figures out what the user must know, what the user is aware of. And now when the user is in a problem, it figures out how to help solve the problem. It gives actually useful advice. It actually worked. It was in its demo version. People were very excited by it. And then the Microsoft lawyer said, wait. You're going to be recording what the user is doing and recording that? No way. So they said you can't use any background material. Just sort of figure out, and this was based on a Bayesian net. But you can't actually record what the user is doing. So okay, fine. So this Lumiere project became this guy, which we all agree doesn't work very well. It was sort of a lobotomized version of a very good product, lobotomized because of the need to preserve privacy. But it was a really good tool at one point, and it still uses a Bayesian net, although it's pretty hampered nowadays. Oh, I'm sorry. Do people know this guy? Okay, good. So I don't have to explain. Other products, Microsoft's pregnancy and childcare tool was also used Bayesian nets to help do diagnosis of what's wrong with little Johnny. Various troubleshooters for the printers and other software devices were also mentioned and also based on Bayesian nets. There are many other applications. The US Army had a tool that was designed to detect battalions from side aperture radar and other information, as well as topography. NASA, the space agency, had a tool, a decision support software tool, that used Bayesian nets to do diagnosis of space shuttles. GE, General Electric, had a tool for monitoring utility generators that again used, in this case, decision networks to figure out what was probably wrong with the generator and try to anticipate the problems before they actually became problematic. Intel, that company that makes chips, had a very cool application. They looked at chips that were designed, and they did testing at the end of the fabrication process. And if there was a problem with those chips, it tried to figure out that chip problem was probably due to this stage of the fabrication. Here's where they should go to troubleshoot it. Then there was this company, Knowledge Industry Corporations. There were these two guys at Stanford who were doing MD PhDs, and in their spare time, they started a company that did various medical applications for sleep disorders, pathologies, dermatology, as well as decision support software for capital equipment. Microsoft bought that company, and now they're the people who designed the tools I mentioned earlier. So lots of applications that have been deployed, that have been used, that actually companies were developing and using for real applications. So that was a motivation. That was saying these tools are actually being deployed, being used. Let me say a bit about what they are. what is a belief net and how it's basically a factor distribution. I'll define what that means. Give some of the semantics. I'll talk about how to use them, how to do inference from these tools, and some applications. I already talked about a few. I'll say a bit more at the end. Talk about other models. I probably won't get to learning about these. If you're interested, come talk to me. I've got other talks on this material as well. But I'll cover these material in this order. I'm going to assume you know this part, but let me actually give a little example. So probability 101. Just imagine you have 100 individuals, and some of them have hepatitis, and the rest do not. So here we see a 5 with hepatitis, and 8 plus 87, so 95 do not. And of these 100 individuals, there are 12 who have jaundice, and again, 88 who do not. And we can see that 4 of the individuals, the hepatitis individuals, are jaundiced. So we can now, I'll give some notation. I'll say that this notation means it's the event that a random selected individual has hepatitis, and minus H means does not, and similarly for J for jaundiced. And you can ask some simple questions. Again, audience participation. If I given this data, what's the probability the individual has hepatitis?
5 divided by 5 plus 8 plus 87.
Yeah, 12, 100. Perfect. And there are people who are probability of being jaundiced? 12 out of 100. And not having hepatitis, that's a pretty easy one. And what about these conditional events? Other people who are jaundiced, how many have hepatitis?
4 of 8.
Other people who have, so what are the answers? 4 12s? Yeah. And how about the other way? So these are the same numbers, right? Hepatitis given jaundice and jaundice given hepatitis, the same number, right? No, that's 4/5. They're different numbers. Again, so this would be, as people who don't know, this number here is of the 4 people who have hepatitis, that's hepatitis and jaundice, divided by the total of people who are jaundiced, which is 12. And this was 4 out of 5, 4 out of 5. And this number here, well, that's 8 out of 95. So some quick observations. I assume most people know this already. Initially, there's only 5 chances out of 100 that a person has hepatitis. Once I tell you that they're jaundiced, have yellow skin, it goes from 1 in 20 to 1 in 3. Made a huge difference. That's why doctors collect evidence to say what's the posterior probability of some event happening. Other numbers, again, the chance of jaundice changed when I know about hepatitis significantly. And so you can see lots of it. I assume most people knew this. If you didn't, this is sort of what you'll need as I go on. Any questions so far? So now let's go on to this medical example. A doctor sees a patient and wonders if this puppy, this little guy, has hepatitis, and then does some tests. Decides a patient is not jaundiced, but a blood test is positive. And now wants to just ask the obvious question. For this individual, what is the probability the person has hepatitis given this evidence? How do you go about solving this question? Well, one approach, the probability 101 approach would say, well, I'm going to build a table. I'm going to write down every possible event. There's 3 binary variables. There's jaundice, true or false. There's blood tests being true or false, and hepatitis being true or false. So there's 2 to the 3rd different possible scenarios, possible worlds we might live in for this individual. And everyone that has a probability. There's 64.5% of the people don't have hepatitis, have a negative blood test, and don't have jaundice, and down to 3.8, where all 3s are true, and then all the other numbers here. The real world's one of these, so these numbers all add up to 1. And I'm done. I've got these 8 numbers. And for this question, or any other questions, I can just marginalize and conditionalize and get the answers. So for example, if I cared about the probability of the people who are jaundiced, what's the chance of having a negative blood test? Well, that's a probability of not having a negative blood test and being jaundiced. So it would be having jaundice and a negative blood test. So it would be, so the denominator would be the chance of being jaundiced, which is these numbers, and the numerator would be the subset of that. So what's the probability of not having a negative blood test and being jaundiced? It's the sum of these two numbers, and the denominator is going to be some of these four numbers. So it turns out to be 85.7%. And I'm done. I could just use this table and get any answer I want for discrete distributions. But there are some problems. One is, that's a really weird table. Do people think about, these unconditional events? Do you think about, the chance of someone not being jaundiced, having a positive blood test, and having hepatitis? I would say not so often. It's more natural to think of conditioning events. Of the patients with hepatitis, how many were jaundiced? That was the little demo I gave earlier. Of the case where the battery was bad, what's the chance that the lights of the car will be dim? That's a more natural encoding. That's a more natural way to think about the world. That's one problem. Anybody think of another problem with this table? How big is it? So this argues for conditional events. The other is, if I have 3 binary variables, there are 8 numbers to represent. Well, 7 because it adds up to 1. What if I had 10 binary variables? Now how big is the table?
2 to the 10?
Yeah, 2 to 10. And, let's say it's binary, so 2 to the 10.
Oh.
Yeah, but you're right. So it would be 1,000-ish. I'm not scared of 1,000. What if you had 30 variables? 30 binary. That's 1 billion. I'm getting a little scared, right? I've got fast machines and machine learning algorithms to try to find these, but that's a lot of numbers. That's the other big issue. It's just, it takes an exponential number of numbers to specify this. So inference, we're going to see, is very expensive. You're going to have to do marginalizations, adding up an exponentially large set of them. And the other issue is, how are you going to acquire it? You're going to ask. I can imagine going to a doctor and saying, I've got 8 questions to ask you, and then we can start doing diagnosis. I can imagine doing that. You go to a doctor and says, I've got 30 variables. I've got 1 billion questions to ask. We start now? I suspect they won't talk to you again, or at least they might ask a grad student, but maybe even not that. So you really can't get by with this number of numbers. And in fact, back when I was growing up, way back when, this was the death knell for probabilities. You just can't possibly do it. You can't imagine having billions of numbers. Therefore, the whole field is just misguided. There's no way you can use probabilities. Try other approaches. Well, no. Turns out there are ways you can just use some of the connections. There are ways you can just find, you can factor the distribution and just use the factored information. And that's what leads to Bayesian belief nets. So I'm going to show you a way to solve. I'm going to have a way to look at just conditioning events that are natural to express, and just a subset of those that I need to solve the problem. I need to represent the world. So how do we do this? With a graphical structure. This is a trivial belief net. It's a graph model with nodes and arcs. The nodes correspond to variables. H for hepatitis, B for blood, J for jaundice. And the links, they're sort of statistical correlation. Think of it as causal dependency. It's not quite right, but that gives the right motivation for what's going on. So this is a network. It's got one more thing that makes it a bit more complicated. These so-called conditional probability tables. These are the numbers that quantify their dependencies. So some make a lot of sense, right? You look at this one immediately and say, this is saying the probability of hepatitis being true is 0.05. 1 in 20 of the patients in this clinic presumably have hepatitis. And these add up to 1, so 0.95 do not. This table also kind of makes sense, right? This is saying of the patients who have hepatitis, 95% of them have a positive blood test, and 5% do not. And of the patients who don't have hepatitis, 3% still have a positive blood test. So sort of sensitivity and specificity information. So that makes sense also. What about this beast over here? What is this showing? This is more complicated. This is saying for every parental assignments, for all the parents of jaundice, it's going to give you probabilities. It says, of the patients who have hepatitis and a positive blood test, 80% are jaundiced. And of the ones who don't have hepatitis and a positive blood test, 30% are jaundiced. So for all the parental assignments, for all the, in this case there's 2 parents, there's 4 different assignments, it gives me numbers. Okay, does that make sense? Any observations about this table? Yeah. So if you look at it, you'll see that, well, so a first comment I want to make is, I don't really need these numbers. This side, this is just 1 minus that. So that's just redundant. So I'm going to re-represent it by just putting the positive outcomes. But now look at this. Now it should be, do you see any pattern in this? Yeah, 0.8. So 0.8 was the probability of having of being jaundice given hepatitis. And the blood test just didn't matter. And what about this other one? If you don't have hepatitis, there's a 30% chance. And once again, blood test doesn't matter. For both situations, the blood test was superfluous. Again, this is my animation, right? So the probability of jaundice given hepatitis and blood test being false is the same as jaundice given hepatitis and blood test is true for all the assignments. Which says basically, once I know hepatitis, the status of hepatitis, the blood test doesn't interfere, doesn't tell you anything about the jaundice, about being jaundiced or not. It's redundant. That is, jaundice is independent of blood tests once we know hepatitis. This is a critical part of this description. And we can use that to say, well, we don't need this arc. We can get by with more animation. Oh, you see how it's going to disappear, right? Okay. So you can get by with this simpler network, one which didn't have the redundancy that was present in the original network. So this is the first sort of non-trivial network structure. It has the same information as the earlier one, but has a smaller number of numbers. Notice I only needed 1, 2, 3, 4, 5 numbers, not the original 7 to represent it. It just requires sort of the simple actuarial information you might get, 5 parameters. You can do computations, we'll talk about that later on, just with the numbers here. But I want to just emphasize sort of what I said quickly a moment ago. Maybe I'll go back to this slide actually. This once we know hepatitis. I'm not claiming that jaundice and blood tests are independent. They are not. If someone is jaundice, that suggests the blood test that the person has hepatitis, which again gives evidence to support the claim that the blood test is positive. So just this information is correlated. There's a dependency. What I'm saying is, once I tell you the hepatitis status, now these are decoupled. So when I said that, let me go on to I had a colleague who used to describe this saying, let's talk to the Bayesian net. Let's do this conversation. So here we can say, so the baby's name is Fred. What's the probability that Fred is jaundice, given no information in this network? And the Bayesian net can do a computation. Say it's 0.325. So that's the probability, given no evidence of that the child is jaundiced. By the way, there was a blood test administered. Now what's the chance that Fred is jaundiced? And now, given the blood test is negative, the chance of jaundice has changed. Again, not having A negative blood test suggests he does not have hepatitis, which decreases the chance of being jaundice. That all makes sense. But let's go on. What's the chance of jaundice given hepatitis? So again, that's another number. Again, it went from 0.325 to 0.8. It increased tremendously. But now the kicker. What's the probability of jaundice given hepatitis? Oh, and by the way, the blood test was negative. Who's paying attention, right?
Doesn't matter what the blood test was.
Exactly. Which means it just depends on that. So the answer is 0.8. Yeah. So again, so what's the take-home message? Jaundice does depend on blood, right? If it was independent, then this would be the same number as that. But they're not. There's a dependency. But once I tell you the hepatitis status, now it factors. Now the blood test, as someone said, did not influence it at all. Made no difference. Does that make sense? This is a, while standing on one foot description of what Bayesian nets are. You get this factoring. Questions? Blood does depend on jaundice. We saw that only through hepatitis. We saw it also again. So again, blood and jaundice are correlated. There is a dependency a priori. But they become uncorrelated. They become factored once I tell you about hepatitis. Okay. So this is an example where symptoms are independent given the disease status, which happens a lot, though not universally. Let me give another example. You have kids, young kids. So if I find that a child has just bought size 5 shoes, I could probably guess how well they read. Because they probably are 5 years old-ish, they probably are at kindergarten level. And if they have size 10 shoes, children's sizes, they probably are in grade 5 kindergarten. So shoe size is coupled, is dependent, is correlated with reading ability. Does that make sense? But not quite, right? Once I tell you, here's Johnny, he's 5 years old. Does he have big feet? Well, of course you wouldn't say that, right? You guess it. Once I tell you the age, that decouples it, right? So if I don't tell you age, reading ability is correlated with shoe size. Once I tell you they're 5 years old, I can guess how well they read. Big feet or small feet doesn't really matter, as far as we know, as far as medical science tells us today, right? Okay. So this is another example of a simple factoring. So what's going on? So this idea of independence. Independence says that if I have a coin and I toss it multiple times, there's a certain chance of heads the first time. And once I saw it was heads, I flip it again. The chance of being heads the second time is independent the first time. If I know it's a 0.7 coin, it's 0.7 the first time, 0.7 the second time. That's independence. Once I observe that it was a heads the first time, there's a 70% chance of heads. The first coin toss was tails, it doesn't matter, it's still 0.7. This is independence, and there's lots of ways to describe that. That happens. Dependence is a useful notion. It does happen sometimes. But what's much more common is conditional dependencies. So shoe size is not independent reading ability. I went through this the same way. Blood test is not independent of jaundice. But once I tell you age, they become factored. That's conditional dependence. That leads to factoring. So again, I said in words, but there's some nice formulas, right? So this would be unconditional independence of alpha and beta. Factoring just means if I condition on gamma every place. So this would be a conditional independence. And that happens a lot. And that's what Bayesian nets and Markov nets and probabilistic graphical models in general, that's what they're capturing. And that lets you reduce the dimensionality, lets you express things more laconically and understand what's going on. Let me give a bigger example. I gave a toy example with just 3 nodes with hepatitis and jaundice and blood tests. Let's imagine a bigger one to see some of the power that comes from having more extensive network structures. So you can ask questions about this structure. You can say, for example, does being jaundiced depend on being alcoholic? Oh, I'm sorry. This now we're going to say hepatitis can be caused by being alcoholic or having sort of viruses. And hepatitis, again, leads to jaundice in blood tests. And now you can look at, again, I made up these numbers, by the way. I'm not claiming 32% alcoholics in any particular population or virus attacks, but these are numbers that sort of have the right qualitative descriptions. We can now ask questions about this structure. So I started saying a moment ago, if someone, what chance someone is jaundiced, a certain number, I tell you, oh, they're alcoholic. What do you think happens to that probability of being jaundiced? Stays the same? Goes up. What if I tell you the person does not have hepatitis? What's the chance of being jaundiced? There's a number. Oh, by the way, they're alcoholic. Does it matter? Well, that's exactly the notion. It becomes decoupled. Alcoholism causes, in quotes, leads to an increase in being jaundiced. And hepatitis leads to jaundice. So you can show that there's sort of a connection there. So if someone's alcoholic, you expect them to become jaundiced, but only via hepatitis. I tell you the hepatitis status, I can predict the probability of jaundice. What happened above doesn't really matter anymore. It's been decoupled that way also. Okay, questions? Yes?
So if I'm given the blood test but not hepatitis, and I want to calculate the probability of jaundice, is there an easy way to do that using the...
Yeah, they're computational tools, and I'll say a little bit about them. But yes, you can recover the original joint and use that, but there's more effective ways of doing it. Okay, other questions? Okay. And let me give you a more macabre example of where, so Bayesian has this nice property that if there's a way to factor distribution, it can exploit it. Sometimes there is no factoring. So here's a macabre example of a family history of depression might cause a mother's suicide as well as you being depressed. And a mother's suicide by itself might lead you to be depressed. Sorry, it's such a macabre example, but you can imagine statistics like this. And remember earlier, I had numbers that were the same. Here they're not the same. Here, there's actually a dependency that independent of the family history of depression, suicide, a family suicide might lead you to be depressed. So again, just pointing out that in this context, this is still a Bayesian net, but there's no factoring. This required all 7 numbers. Remember, if it was represented as a table, there would be 8 numbers. It adds up to 1, so it's just 7 independent numbers. Here again, there's 7 numbers to represent it. There's 1, 2, 3, 4, 5, 6, 7. Okay. So, I'm sorry. Yes.
In the case of something like that, is there a way to approximate the inaccuracies that accumulate if you assume independence, if you have some measure of how off you're?
Yeah, so good question. Yes, there are ways to talk about the sensitivity. There are ways to estimate it from a Bayesian point of view, as well as just by putting numbers. You certainly could do something as simple as just marginalizing this out and just removing this arc and getting numbers and just looking at it. Yeah. And looking at the structure, at the difference of these individual numbers from the variance. You also could ask for a particular question, what is the sensitivity? And I've got some results about that from back when I was little, right? Okay. But good. Other questions? So what's the advantage of these belief nets? Well, basically, they are based on solid standard probability theory. I won't talk about other models that people have proposed for simplifying something like distributions. This is actually the real probabilities. All the advantages you get by solid semantics induced by probability theory comes along with this tool. You can look at it and say, what depends on what? You can actually look at it and say, I can read it off and say things about what factors are part and what things are dependent. There's also efficient encoding. Oh, I didn't mention earlier, I should have said earlier, that when I had this picture here, there's 5 binary variables. So if I write the whole table out how big would that be? 32, well, 31 independent parameters. Here there's 1, 2, 6, 7, 8. There's 10 numbers. These 10 numbers to encode a 31 value. So it's a 10-dimensional manifold in a 31-dimensional space, basically. That's still, you can still use for reasoning. And that was a point over here about numbers. And that may not be that impressive, but there's examples of the CPCS network, which has, if you represent naively, it has this number. How many atoms in the universe are there? It's that type of.
It's much less than that.
Oh, yeah, okay. So yeah, so you couldn't really represent it, even if you tried really, really, really hard, right? And here you get around like 8,000 numbers. It's still a large number of numbers, but you can imagine actually learning that from a data set and representing it. Okay. There's ways to learn, which I won't talk about today, but I've got the material on that. So what do you do with that Bayesian net? So one, you can look at it and see what depends on it. You can also answer questions. So this is called semantics, so looking at it and saying what is it actually expressing. And this is inference. How do you use it to answer questions? What's the chance of cancer given certain factors? Or maybe what's the most likely interpretation given what I just observed? We'll talk about those. Good time for questions here. Are people tracking it so far? Okay. All right. So semantics. So remember, it's a Bayesian belief net is a direct acyclic graph. It's a graph whose nodes represent variables, whose arcs talk about dependencies. They're directed arcs, so from parent to child or from a set of parents to a child. Conditional probability table, which are these numbers that talk about sort of the conditional probability of a child given its immediate parents. And that sort of quantifies how the effects of a parent on a child. Parents in this graph theoretic sense. And again, I should mention, this is another example. One of the founders, one of the fathers of probability of Bayesian nets, is a guy named Udaya Pearl, who lives in Los Angeles, an area known for burglaries and earthquakes. And so he has a little network he uses to describe it. And he has a network here which talks about chance of burglaries or earthquakes happening, being very sparse. Chance of the alarm in his house going off, if there was a burglary or alarm happening, high probability. And alarms go off by themselves anyway, right? And then he has neighbors, John and Mary, and John calls if the alarm goes off sometimes, but not always. And John just calls and chats some other times. And Mary calls also if the alarm went off. So that's a simple network that Pearl talks about. So what causes John to call? Well, he calls because the alarm. He doesn't know there's a burglary. He just hears the alarm in the next house over. Why does, again, there's probabilities here. Mary doesn't always call when there's an alarm, and only call if the alarm goes off. Well, again, she might not be home, and the phone might be broken. So those probabilities make sense in this context. What comes next? And you can see in dependencies, again, as you saw earlier, that I'm taking this model that says burglaries and earthquakes are independent, right? that burglars don't cause earthquakes to happen, and as far as we know. Also that burglaries lead to alarms happening, and that leads to John calling. But you can now observe that John and Mary's calls are coupled. John calling probably suggests an alarm, which means Mary might call also. But once I tell you that there's an alarm, then these things are factored apart. Okay, and that's what I just said a moment ago. Oh, and this notation, I should have said, this is the notation for independence. Burglaries are independent earthquakes. John's calling is independent Mary calling, given alarm. All right. Oh, okay, well, a little bit more technical stuff. I'll make a comment that these nets have this local Markovian property, which is a mouthful. It says that a variable is independent of non-descendants given its parents. I think for interest of time, I'm going to go really fast through this and just say that there's a way you can look at this network and understand what's going on. I've got pretty pictures, but I'm going to just say that there's a way you can read off what's happening. So the bottom line is, if I want to compute the probability of a tuple of A, A is true, of A is true, and B is false, and C is true, and D is true, that tuple, I can compute that probability by looking at a node given its parents. Again, I've got slides that talk about it, but for now, I want to say that you can look at that and understand this. So this is a chance. What's the problem that John calls, Mary calls, there is an alarm, there's no burglary, and no earthquake. So again, the slides I skipped had just said that it's always true. Forget about Bayesian nets. It's just a statement about probability that this this tuple is the probability of John calling given all the evidence, all the other factors, times the probability of Mary calling given the remaining terms, times probability of alarm given the remaining terms, times burglary given the remaining terms, and earthquake. So that's just always true. That's just a statement about how probabilities work. But because of this Bayesian structure over here, you can do something with it. So I made the comment that that a node is independent of its non-descendants given its parents. So if I give you a node given a bunch of non-descendants, so there's John callings, everything, its descendants are over here, so everything's a non-descendant. So John's calling is independent of everything else given his parent. So this hairy expression, this given all these, that corresponds to John calling given his parent. What is John's parent in this structure? So this big mess, John's calling is independent of Mary calling, burglary, and earthquake once I know the parent, alarm. So this thing reduces to that. Again, I skipped 3 or 4 slides, but what about this? So Mary's calling is over here, and that's independent of its non-descendant, so everything's a non-descendant of Mary calling, given her parent. So what does this reduce to? Okay. So alarm is independent of all of its non-descendants, of not these two, everything else, given his parent. Alarm, its parents. Okay. So how do I reduce this? You guys are too good, right? Okay, finally get to burglary. Burglary is independent of his non-descendants. So burglary given his parents, so what is its parents? It's unconditional. And this guy, how do I reduce him? Well, that's the way it is. Okay. So I took this big hairy expression, this thing in about 5 variables, and said this can be represented in terms of basically, one term for John, one for Mary, one for alarm, one for burglary, one for earthquake. And each case, it depends just on the immediate parents. So it reduces to this. And in fact, in general, this is true in general, that you can always write this. So the probability of this event would be, well, I did all the animation. So this thing is 0.9 is 0.99 times 0.02 times 0.29 times 0.01 times. So basically, I can write this complete tuple as sort of, it's like a Chinese menu. 1 from column A, 1 from column B. It's 1 from this one from that. So I have exactly 1 multiplier from each of the different conditional probability tables. So I can always recover the joint in this fashion. I could just do it for the true assignment and get a number for the true, false, true, false, true, and just get all 32 of them. And I could build that table if I wanted to. There's actually much better ways to do inference, but that would be sufficient. Okay. So comments. So this Bayesian net had 10 entries, but I can recover all 32 values. And in fact, this claiming that the remaining entries are all redundant. Again, it's a 10-dimensional manifold in a 31-dimensional space. To compute, you could get the joint of margin that's conditionalized, but there's other algorithms. And I'm going to tell a little bit about that in a moment. Yeah, that's no redundancy of that structure. So let me get a more complicated question. So far I've been talking about networks and saying there's this way you read off what depends on what. But let me ask another question. what color are my wife's eyes? Okay, some people matter, but let's imagine you haven't met. Well, by the way, I've got blue eyes, right? Does that help? Well, blue-eyed people marry brown-eyed women and vice versa. It doesn't really help. There's actually, again, this model we're taking said they're uncorrelated. Husband's eyes and wife's eyes color are uncoordinated, uncorrelated. Oh, we have a daughter who has brown eyes. Who knows genetics 101? Yeah. So now what happens? I tell you that daughter has brown eyes. What does that tell you about color? So here's a little table, right? This is a standard table which is based on simple Mendelian things. That 2 blue-eyed parents have blue-eyed children, and there's a 50 chance of one has and 25%. It's a simple model. You squint at this, you realize that it does matter now. One of my wife's eye color, blue doesn't help. I have a brown-eyed daughter. Now, in fact, it does help. In fact, you can become dependent. So let's go through a little example. We're going to talk to this network. What color is my wife's eyes? Well, the prior is 80% of people have brown eyes. Okay. I know the husband's eye color. Do you want to know? Don't bother. It doesn't matter. It's 80%. That once I tell you the husband's eye colors, it's 80%, whether it's blue or brown, the husband. But I know the daughter's eye colors. Now do you care? And you say, yeah, it does matter, right? Here's some simple statistics. The wife's eye color is 50% chance of being brown, given the husband blue eyes, and only 22% given brown eyes. It didn't matter. It becomes coupled. Things that weren't coupled initially, so become coupled at this point. But disclosure, our daughter actually is blue-eyed, but the math is easier to describe. Just so people might meet her. Okay. So this is exactly the opposite. So let's go through this, explain this point, right? So here's 3 nodes, X, Y, and Z, and there's different structures. You can imagine arcs that go this way, arcs that go that way, and arcs that go this way. So examples, earthquake goes to alarm, goes to John calling, it'd be this way. And the alarm leading to Mary and John calling goes this way. And the most complicated one is this V structure, where earthquakes and burglaries both point to alarms. And now, given just as part of the structure, what are the dependencies? Well, again, if I don't tell you Z, earthquake and John calling are coupled. Earthquake increases the chance of alarm, increases the chance of John calling. Mary calling is not independent, does relate to John calling through alarm. But here's the most complicated one, right? Earthquake and burglaries are independent initially. So this is if I don't give you the intervening Z. Now let's go the other way. Suppose I tell you that the alarm went off. Now what happens? It's exactly the opposite. Once I tell you the alarm happened, earthquake and burglaries are independent, given the alarm. Mary calling and John calling, independent, given the alarm. But earthquake and burglaries are coupled now. So again, imagine the scenario where, the alarm went off. It's probably a burglar. I better dash home right now. You saw it in your car and you hear the news. There was an earthquake. Well, it's probably not a burglary, right? This is explaining away. I'm not saying there wasn't a burglary, just the chance goes down tremendously. And it's a very common occurrence. These V structures are subtle but very important. I just said this, right? Okay, blah, blah, blah. Okay, so earthquake may explain away the alarm, decrease the probability of burglary. Okay, so again, another sort of mathematical digression. I mean, you can actually look at a graph structure with these direct graphs and read off where are the dependencies. In general, I've got a set of nodes X and a set of nodes Y and a set of evidence Z, and I can say, is it true that all of X is independent of all Y given the evidence appearing in Z? And there's actually ways to do this computation, which involves looking at every node X every node X or every node Y, finding every possible path and saying, is every possible path blocked by the evidence? And it's blocked if either there's this pattern and this is evidence, or this pattern and that's evidence, or this pattern pointing in and this is not evidence. Okay, and again you can, but let's go to a little example. So, car radio and gas. Is a gas tank full or not? So if I tell you, I want to know, there's a chance that the gas tank's empty or not. Does it make sense to say, turn the radio on to find out? That sounds silly, right? Of course, how can that possibly be influential? And the answer is radio and gas independent, given no evidence? And the answer is yes, they're independent. They're de-separated as a term. And you can just observe that if you look at the path here, there's a node here which has two things pointing to, which is not, I don't know the value. Now the next game, suppose the car didn't start. I'm trying to start the car, and it's not starting. It's not starting. Is the gas tank empty? Well, it might be increased. Oh, let me turn the radio on. Is that going to help? Yeah. If the radio doesn't work, that suggests it's probably a dead battery. So it probably wasn't the fault of the gas. And again, the Bayesian would show you this, that the fact that the start is evidence means there is a path from radio to battery. This is one of these junctions. I don't tell you battery status, so it goes through. Here's the spark plug, this status, it goes through. Now here's one of these things where start is evidence, I know the answer, and now again it goes through. So there's a path that goes from there. So these are not de-separated. Okay, a few more examples. Okay, but I'm going to skip those. I'm running out of time. Okay, there's Markov blankets. Oh, okay. So people have cars. Okay, and so you can imagine, engineering one of these systems. So imagine I've got nodes for distributors and fuel systems and car cranks and headlights and spark plugs and battery voltage. And now I say, okay, can you just understand Bayesian well enough to say how these things are related? Tell me the arcs I should draw from here to there. So if you think about it, again, for want of time, I won't go through right now, but you can imagine thinking about it and saying, well, the battery age probably influences the battery, the voltage of the battery, and the headlights working probably depends on the battery voltage, and the voltage of the plug probably depends on the battery voltage, and the charging system probably you could probably, just because of your knowledge about cars, you could probably draw the structure. And in fact, you can draw a structure like this. Okay, so it's 10 of. Let's very quickly talk about inference. Just give a few examples, and then I'll probably wrap up. So I give the semantics. This is what the network is, and how to understand, how to reason about it. But once you have one of these structures, can you do inference? Can you figure out answers to questions? So for example, remember this little example of little Johnny who might have hepatitis given jaundice and blood test. And I give you the structure and these independencies with these numbers here. Oh, and that's a 7, by the way. Okay. And now ask the question, what's more likely, that Johnny has hepatitis or not, given this evidence? So you can compute this, right? It would be, what's the probability of hepatitis given positive blood test and negative jaundice? And I want to find for both hepatitis being true and hepatitis being false. So that's the same as the argmax, so the unconditional version of it. And now we can just work this out, right? So if what's the probability of this for hepatitis being true? It's 0.05 for hepatitis being true times blood test being positive, given hepatitis is true, times 0.95 times jaundice being false, given hepatitis is true. So that would be, hepatitis is true, so it would be 0.2. So it would be this number, 0.05 times 0.95 times 0.2. That's hepatitis being true. hepatitis being false, it'd be 0.95 times 0.03 for the blood test being positive, given hepatitis is false, times 0.7. So it's two different numbers. I compute the products and take the larger of the two values. So here I would say that it's more likely that argmax is not hepatitis because this number is bigger than that number. Okay. So that's one simple inference. Turns out it's much more complicated in general. There's belief assessments, max a posteriori, MPE. So there's different computation you can do with it. And again, there's a lot you can say about it, but I won't have time to say it right now. Just observing that they're hard problems. This one is a fast computation. I guess I have a slide in a moment saying the computational complexity of this task. This one's even harder. And again, there's a system called Netiquette, built by a company in Vancouver, and you can actually have it on my computer. You can actually try it, and you can put values to different things and see things move around. Once I tell you the car doesn't start, you can now say, this is a prior, so the car doesn't start, and now you can see that the air filter goes from 90 to 85% chance of being clean. And the spark quality goes from 25% of being good to 20%. And the starter engine goes from 99.5% okay to like 92%. But now I tell you that, also, oh, by the way, the battery voltage was strong. The force is strong with the battery. So it's strong there. And when you do that, other things change. So that becomes, if this is strong, that means the car didn't start. It wasn't due to the starter system. It was probably due to the air filter or due to the distributor. So you can set values and look at everything else as it jiggles around. Again. So if you can do inference in that fashion, you can do inference in general. You can point to any set of nodes and get answers. You can certainly do diagnostic. Right? The car doesn't start. What's the fault? This is like human diagnosis. I observe these factors about little Johnny. What's the chance he has this disease or that disease? Typically, it's from an observable node, and I try to infer from that some of the nodes that were higher up in the structure. It's causal. I'm about to buy a car. It's an old car. What's the chance it's going to start? This is going from the disease to what manifestations you expect to see. You can do intercausal. This is the explaining away thing I talked about earlier, where if the car doesn't start, the chance of the fuel being problematic is pretty likely. The car doesn't start, and there's a bad filter, the chances that the problems in the fuel system goes from being 30%, 37 to 0.3. You see that? And you explain explaining away. And any combination, you can just point to, I'll tell you this node, and that node, tell me that one. You can do all those computations. Okay. I'm going to skip this just saying that there's subtleties here. For the theoreticians in the audience, right, Bayesian inference is complicated. It's NP hard to get the right answer. It's easy putting 3 sat there. In fact, it's sharply complete. But what if you say, I don't care the exact answer. Give me an approximation to it. Give me 1 bit. Is it bigger than 0.5, less than 0.5? That's an NP hard problem also. Even getting 1 bit of the right answer. In fact, even if you want to do it stochastically, you want to have with high probability, greater than 1/2, you get 1 bit. That's that's not going to be possible at polynomial time unless p equals rp. So it's a really hard problem. But there are efficient ways to handle certain class of problems like polytrees. I can talk a lot about computing probabilities. So have you heard about hidden Markov models and common filters? The reason why it's so efficient is to use something called the polytree algorithm, which is a fast computation. There are approximation methods. Interested, teach a class on them. I spent a whole semester talking about this type of things. But not right now. I should just wrap up here. But it's a shame because this is an important part also. Unless, do people have to leave at 1 o'clock? Should I go on and say more and abuse the, Mr. Camera person? You've got 1 more minute of film, right? Okay. Film. Do people have film anymore? Okay. So if people, let me pause. If you have questions, ask them now. Otherwise, I'll say a little bit more about this and go a little bit over. People have to leave. I'll look over here so I won't notice. Are there questions people want to ask at this point? Yes.
If there are two things wrong, like
Yep.
with health problems, I always hear about that. We
Yeah.
didn't catch this because we
Yes.
thought it was that.
Yes.
Then you wouldn't have this problem, right? You could actually
You can
use the probability.
you can compute the posterior probability of multiple factors, and not a single node,
At
but
least quantify that risk.
you can be explicit and say the probability of A by itself is this, probability of B by itself, the probability of A and B both being true, or A being true and B being false. You can ask all those questions. And in fact, if I could have shown you the Bayesian net, that little Netiquette example, you actually see explicitly that all nodes jiggle. You can look at that quantity. Good question. Other questions? Yes.
So how often does meta-analysis do this wrong? The causal inference.
So a few comments. So one, you put the correct data in a Bayesian net.
Yeah.
It gives a computation, it gives the right answer. But that assumes you have the right structure and the right parameters.
And are using Bayesian techniques.
Well, that I'm not going to question, right? That's like saying, imagine Modus Ponens stopped working. That's just that's not the world.
No, that they know to use Bayesian net.
Oh well, if people don't, if people use other tools, that's their problem, right? I can't take responsibility for people who use alternate facts or alternate reasoning
Because
methods.
I think this was behind some confusion over vitamin D dosages and osteoporosis
Okay.
in the last couple of years.
Okay. I could easily believe. I mean, garbage in, garbage out. You put the wrong structure.
Yeah.
No matter what you do, you might get the wrong answer. The right structure and the wrong parameters, you've got problems, right? The right parameters, there are ways to get sensitivity analysis. If this parameter is off by 0.2, how does that affect it? And I've done some work along those lines in my younger days. Other questions? Okay.
So Russ,
Yes.
in every case you compute the probabilities from databases that doctors, for example, will have, or where the probabilities come from.
So, great. So, remember I said there's one part I'm not talking about, which is learning. So there's a part which says you have a database and there's a way to come about and produce the structure and the parameters. Not talking about that now. I have another hour and a half talk on that. Right? I've got a whole semester long class on this topic. So I'm assuming that you woke up this morning with divine inspiration that says, it's this structure, that's 0.2.
Okay.
Yeah. And so, again, if that's wrong, you're in trouble. There are reasons why you might not want to use the correct structure because it'd be too hard to get the parameters right because there's too many degrees of freedom. So that's another whole topic. Another thing common is you might not want to have the exact right answer anyway because you won't be able to estimate all the parameters. Yeah.
So some of the most powerful probabilities will be the smallest ones, or the rarest.
Well, the ones.
In which case, the measurement error is really, really bad.
Yeah. It's not the Bayesian fault, right? Yes, they're really hard. It's right to estimate rare events. That's true. And you're screwed, right? But the nice thing is things might factor. You might have this being 0.2 and this being 0.03 and that being 0.07, that being 0.9. The product of these is like 10 to the minus fifth. But that's okay. You can reason about the 0.2 and the 0.7 and get the data independently of those. So it's not the probability of a complete event, it's of the individual things. Now, if each individual thing is 10 to the minus fifth, and you have 100 examples, you probably have never seen any examples. So all the estimation problems come in for that.
And no one can do better than that.
Again, if with divine intervention you could do better,
Yeah.
if you're willing to, I mean, people have tricks that you can try to pretend you get examples, but if an event's very rare, that's a problem. And it's not the Bayesian's fault, right? Good questions. Let's spend a few minutes about MEU. So far I've been saying you've got probabilities and you compute numbers. What do you do with them? It's nice having this 0.7 or 0.03. Do you operate or not? What minimizes risk? What actually is the best action to take? And there's this MEU, maximize expected utility principle. And you can show under fairly weak assumptions, this is the best thing to do. Might be the best of worst options. Think of voting, right? I'm not saying but you can imagine multiple options saying which action is the one that's going to be the best one. And this way to quantify what best means. So again, the game here is I've got some observations and a set of actions. Think about take 2 aspirins, call me in the morning. Do surgery. Take this drug. There are a bunch of actions I can take, and I want to compute the expected utility of the actions given the observables for each of the actions, and I want to take the largest one of those, and I'm going to return that. So that's it maximizes the expected utility of an action after the state that occurs after taking actions given prior observations. I'm going to skip this, just saying that this idea of maximize expected utility is actually a pretty good idea, and it's not utility squared, it's not mini-maxing, it actually is finding expected value. So let me give a little example. But first I need to give some notation. So I talked about Bayesian nets. Bayesian nets, belief nets, you have chance nodes, and I represent those with circles. These decision nets also have some other types of nodes. So one type of node are chance nodes, like the state, the observables, and other states. So the state, this could be a state I'm in right now, and what I observe given those states. So the state might have, a person might have cancer. I can't observe the cancer. I can observe the genome. I can observe other clinical factors. So that's what this is representing. It's a chance nodes. I can't influence them. I can just observe them. There's also decision nodes, action nodes. This is, I choose to make an action. I choose to do nothing, or I choose to operate, or I choose to give a treatment. These are squares in this case. These are decisions I get to make. So the third type of thing are these utility. This is how good is it if I do this? So the way to interpret this is, there's some distribution of states, of state A, B, or C. The patient is cured or not cured, right? And you can see how happy I am if he's cured versus not cured. Presumably I'm happier if he's cured than not. But again, these would be a set of numbers. So to make this concrete, let me go through a little example. So here's an example. There's 80% chance, or 20% chance that the patient has a certain disease. That's what this represents. There's a treatment you can take, treat or no treat, and there's a chance of relapse. And here's a little table. It says, if he didn't have the disease, you don't treat him, there's a 0.1% chance of getting the disease. And something, whether you treat him or not doesn't make a difference. More interesting, if he has the disease and you do nothing, there's an 95% chance he still has the disease. But the good news is, if you have the disease, you treat him, there's only 1% chance he still has the disease. So that all makes sense, right? And the utility. How happy are you if he has a disease? Well, you're negative 1,000 happy, right? This is not a good thing. And here you just, it's zero. I mean, I'd rather not lose $1,000 rather than lose $0. So this is a simple, a trivial little decision net. And now you can ask questions of, I get to decide whether I do a treatment or not, which is better. And again, there's some math over here. Don't get scared. It's just using the numbers that appear here in various ways and multiplying this and adding these and computing the probability. If I do a treatment, what's the chance of having a relapse? And so I'm going to compute those numbers. And it's the numbers 0.0028 if I do the treatment. And the chance of no relapse given treatment is 0.9972. It's 1 minus that. And similarly, if I don't do a treatment, what's the chance of a relapse for these numbers? Again, same I mean, I multiply these numbers and add them up, blah, blah, blah. It's all just a simple computation. So now, given these numbers, we can go back to this picture, right? These are the numbers I had earlier. I now compute the expected utility of doing nothing. The happiness is negative 191. The expected happiness of doing a treatment is negative 2.8. What should you do? Treat. But it's $2. Yeah. I'd rather it's $2.80 rather than $190. Yeah, so you can actually decide on the best action. And this can be based on multiple diseases. You can look at multiple factors, look at sequences of tests you can run. You can make decisions about what tests to run to get information to make decisions downstream of what actions to take. So with this model, you can now represent actions that change the world, like treating, actions that sense the world, like paying money to do a test on somebody. All in the same framework. Okay. Extension. Yeah. Okay. So I talked about simple examples with binary variables, but you can have larger domains and Gaussian variables. I talked about decision nets, also influence diagrams. Okay, lots of other encodings. I think I'm going to skip this. I've already talked about most of these already. But other examples that have been measured and deployed, types of tasks, examples of things that have been done. So this is the troop detection system. Here's one for looking at car insurance, and one to look at QMRDT for medical diagnosis with a bunch of diseases with 40,000 arcs, sort of a bipartite graph between disease states and observables. And the one I mentioned earlier, the CPCS system, predicting oil prices, and the real system, which is a little more complicated than that. Predicting when you should plant potatoes, depending on planting date and anyone know what home destruction date means? No farmers here. I don't know. I mean that. Okay. Warning systems. Here's a decision net saying when a warmer should go up for a particular power plant. Other models.
Which of these were automatically generated versus, I mean, you could imagine a human drawing maybe 10 or 20.
Yeah. The ones I just showed, these ones are pretty much, these ones were hand drawn, but the parameters might have been instantiated by observations. So again, talk on learning, I'll talk about learning structures and how you can learn structures de novo from just data, learn structures based on a human giving them to you. And also talk about how you find the parameters of a given structure and how you handle missing data. So lots of stuff there. But yeah, for the ones here, I'm pretty sure these ones are all done by hand, the structures at least.
But in the real model, the arcs are built just based on distance and the probabilities.
The arcs are built by someone saying, remember the example with the cars, right?
Yeah.
You sort of, you could draw any, you can have data that does anything you want, but I know that the car starting depends on electrical systems and the fluid systems and so forth. And I know that the battery influences this and that. So you can imagine just looking at it, based on your knowledge about cars or about the mechanics, how things should be connected. But if you don't know that...
Computational terms, the computer can only look at the probabilities, right? The correlations between them.
Well, the standard model is, here's a bunch of data. Here's a bunch of examples of cars braking and different factors in that, and trying to find the correlations. Or the medical cases, right? Here's the person's genome, or a subset of the genome, and this is a disease state. Can I find the pattern, the connections which optimize the log likelihood, which is the way you learn the structure for these. So again, if you're interested, I can keep talking. Now, there's other talks about how you actually learn these structures and learn the parameters. Good. Maybe just one observation. Back when I was growing up, we had rule-based systems. That was the way the good Lord intended people to look. And none of these probability values. And rule-based systems would have nodes that describe different factors. So you would have a rule that says, for example, jaundice implies hepatitis. And you have like certainty factors or CF or something to quantify it perhaps. But it's interesting that a rule-based system typically goes the direction you think about. You put in observations lead. Maybe it's time to. The observations lead to certain conclusions, and that's backwards from what Bayesian nets typically do. Typically, we say it goes the other way. Given a disease, what's the chance of observables? I'm going to use it the other way. I'm going to use it saying, given observables, infer what the state of the world is, but I still represent it with the other direction. So that's sort of interesting. It turns out it's easier for people to think in this causal direction, that hepatitis causes jaundice, even if you're going to use it in the other direction. Given jaundice, what's the chance of hepatitis? Okay. Blah, blah, blah. Okay. Belief nets and neural nets, they both have graphical structures. My distinction between these two fields is, my distinction is that you have to, within a graphical model, it's a model. You actually have nodes with semantics. That may be latent, but they have semantics in it. I'm saying I should probably wrap up, huh? Right? Okay. All right. So there are reasons why neural nets work effectively, but a Bayesian net, a graphical model, it's easier to initialize it because you have some semantics what's going on. Okay. Yada, yada, yada. Okay. Markup, that's what I'm talking about. So what I talked about here, I think about this three-dimensional space. There's directed and undirected models. There's discrete and continuous distribution. And there's semantics, inference, and learning. I talked about directed model, Bayesian nets, as opposed to Markov nets, undirected. Discrete, which are true or false or ABC rather than the Gaussians. And I just talked about semantics and inference. There's a whole bunch of learning. There's a whole bunch I can talk about in that context, which I won't do. Summary slide. For almost every real application, you have to have probabilities to reason about the world correctly and effectively. If, in general, there's a combinatorial explosion if you want to represent all the minutiae, all the minute details, there are ways you can think about factoring the distribution by exploiting the fact that you want connections and just some of the connections, and that leads to belief nets. It's a proven technology with many deployed applications and many different types of areas, and there's some still remaining challenges about making inference more efficient and more ways still to have learning work effectively. I'll end there. Thanks.